Welcome to Get Started with Essential Chemistry Part 2, Hands-on Investigations. So I'm assuming that you've seen Part 1 where we talked all about the ebooks for the ebook and the lab book for Essential Chemistry. We're going to focus mainly on the hands-on investigations today. So I wanted to, as a reminder, that you could sign up again to see Part 1 if you haven't seen it before, or watch a recording of a previously delivered session if you go to pasco.com/training. The agenda today, there's quite a bit on here, so I might not get to everything, but I'm going to get through as much as I can. I'm going to do a quick review of the lab investigation resources that are in the Digital Essential Chemistry Lab Book. And we'll pick up where we left off with the Investigation 11A, evaporative cooling. That was with the cotton ball and water and alcohol from Part 1. Then I'll talk about the types of equipment you can get in the equipment kits that are built to go with the Essential Chemistry curriculum and the SPARKvue software, followed by Investigation 8A, it's a stoichiometry lab determining limiting reactants. And in that, I will demonstrate shared session, where if you're attending live, you could jump in if you'd like. Investigation 12B, Boyle's Law. So this will be an example of how to collect data manually with collecting data points one at a time versus continuous data collection. We'll also look at mathematical modeling and what's the purpose of doing linear fits. So if you're, we'll cover everything from the basic chemistry analysis techniques all the way through some advanced things for high school level, such as curve fitting and using mathematical models. We'll look at, okay, so if we're not doing one of the essential chemistry labs, how do we just do a off the cuff, on the fly investigation with sensors? That will be an informal investigation with pH of household substances. We may or may not get to this last one, investigation 3C, physical or chemical changes. But if we don't have time to do it, I'll point you to the Academy, the PASCO Academy, Chemistry Academy that we talked about in Part 1 to show you how you can still see it. If you'd like, you can get the materials for this presentation from that link. Let me paste that in chat so that you can have this presentation available to you. There will also be some, sometimes you'll say, hey, I'll say, here's a resource. It's in the shared resources. Here's what I mean. If you went to that website, and by the way, you could scan it with your phone and get there too with this QR code, and keep my mouse away from it so you can actually get there. So if you go to that link, here's the presentation that you see on your screen, same one you're looking at, and then a resource folder in there. There are some little cheat sheets like how to get help on SPARKvue, how to get help with shared sessions, and some pH and calibration and care tips. All right, so let's begin. Quick refresher of what's available in the Essential Chemistry program. At the base level, you can get just the digital ebook, which would include the digital resources that we're using today for labs. You can add on a print copy of the student textbook. You can add on a print copy of the student lab manual or teacher print lab manual. You could add on equipment, and this is just one of the available kits that's shown here. And what's included with the digital Essential Chemistry program is teacher ebook with student assignments, including a lab book, an infinite test bank, infinite meaning that the quantitative questions can be regenerated with different versions so that it reduces cheating between students. The PASCO Chemistry Academy, which is a way for students to experience the lab offline, and the SPARKvue software app that we're going to use today to collect and analyze the data used with sensors in the kits. So everything in blue here is automatically included if you're a PASCO Portal subscriber. And PASCO Portal is a subscription service that makes it easy to share digital resources with your students, especially in your learning management system like Schoology or Canvas. It also has the ability to work with your single sign-on to get in there for teacher resources. However, the student ebook is not automatically included with the PASCO Portal subscription. You would have to buy a separate license for the student ebook, but again, the teacher book is included. So here's what you see in the lab book. The lab book, which is very similar to the textbook. You'll see a slide presentation that goes along with the lab procedure with an introductory question called Think About It, this goes with every lab. There's always a think about it slide that gets students engaged and thinking about what are the concepts and how do I think through the challenges in the lab ahead. There are the way all the labs are presented is there's two parts to it for students and also teacher version as well. So there's the lab directions document, which is step by step. And then there's a separate answer sheet, which has questions and place to draw graphs and enter data in tables. And it's basically the answer sheet is what students fill out with their data and analysis and questions for a conclusion. The teacher versions will have lab preparation. For example, you see in the picture here, there's a diagram of the stopper assembly that you would need to put together to do lab 8D, which we're doing in a moment. And it shows how the parts go together, and all the parts are included in the optional equipment kit. It also explains how to make the solutions with the correct concentration and the quantities it'll make. Like, for example, this one says enough solution for 26 students working in pairs. The lab book also has reference materials like these, like safety rules, safety quiz, lab tools, and information and videos on help with SPARKvue. And all sensor-based labs that are in the essential chemistry curriculum include sample data file, unless it's just a digit display lab, and also a video for the teacher to see what's this lab about. Do I want to do this lab? All right, we're going to pick up where we left off. So I'm going to switch my camera to the equipment. We started off part one with looking at a cotton ball wiped on the inside of the arm. If that cotton ball was soaked in water versus what does it feel like when you swipe alcohol, 91% isopropyl alcohol. So students would qualitatively experience and get the experience of they both cool me down, but this one, I think it's cooling, feels like it's getting colder or cooling faster or something. So they take their qualitative step 1, 2, 3 that we did in part one, and now we're going to continue with part 4 forward, using sensors to see, was that my imagination or was it really cooler when I did the isopropyl alcohol? And then further, there'll be a third test with acetone to see how does the acetone compare to the isopropyl alcohol and water, and how come these three substances all behave similarly or differently? Does it have anything to do with the molecular structure, which, by the way, the molecular model set is one of the parts of any of the equipment kits that you purchase includes the model set. So, or actually 2 of the 3 will include the model set. So students further in this lab will go on and build the models of the molecules and look for patterns. So let's begin. We already did step 1, 2, 3 with the cotton balls. Step 4 says open SPARKvue. So here is the SPARKvue application. I'm opening it. And the next step, step 5, I've highlighted it because every single essential chemistry lab will say this step. Open the blah, 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 blah lab file in SPARKvue. They all say that. And the thing that changes is the experiment number and title. So when you're doing an essential chemistry lab, that means if you're already a SPARKvue user, you're probably like, oh, I go to sensor data and I connect my sensor. And that's what you would do if you're just doing any lab or any investigation. However, if you're specifically doing a essential chemistry lab and it tells you something like this, open the number, letter, title, lab file in SPARKvue, that means you could choose a different path. These are paths. There are 6 different paths, 1, 2, 3, 4, 5, 6. The path for essential chemistry labs is open PASCO experiment, that button. So you start here. When it says step 5, open the experiment, go to open PASCO experiment, and then find the essential chemistry folder because this folder contains all of the labs for the entire sensor-based library of essential chemistry labs, pre-built, so students don't have to spend any time configuring the how the file is set up. It's already pre-built and set up for you. So scroll and find 11A, evaporative cooling. There it is. Now say okay. There it is. This is a pretty simple setup. It's just a graph. This would be easy to set up if you were not using a pre-built lab. But the nice thing about this is students are told in the procedure that they're supposed to do something for 1 minute while they're recording data. This file is set up to automatically stop recording data after 1 minute. So little things like that can be programmed into the files, and that's why we have all of the essential chemistry displays pre-built, and that's how you get there. All right, so once you're here, Here is how to connect a sensor. So first you want to turn on the sensor, and this is a wireless temperature sensor. I'm going to turn the power on, and I'm going to go back to my setup. So it's flashing red right now on the Bluetooth icon. That means it's searching for a Bluetooth signal. Now I go into my SPARKvue file and I click the Bluetooth icon to connect that temperature sensor. I wait for it to show up in this menu here. And the nice thing about this is well, let me turn on a different sensor. I'm just going to grab another sensor. Here's a pressure sensor. I'm going to turn it on so that you can see what happens. Look at all these sensors that are on. And what's happening here is they're listed in the order of which sensor is closest to your device. I just moved the pressure farther away. Did you see how it moved down? My computer's actually right below my trays here. So the closest to my computer is the temperature sensor, so that's why it's at the top of the list. So on a Windows computer or a Mac computer, that's what happens also on your smartphones in the SPARKvue app. So now that I know that that's my sensor, there's another way I can check. I have the 6-digit code 060815 that matches the 6-digit code on the front of the sensor. That's right by, whoops, let me back out a little bit. That's right by the flashing Bluetooth icon. So I tap to connect. And if I accidentally tapped somebody else's sensor on accident, I can just hit the X to disconnect it. Oops, sorry, neighbors, I stole your sensor. I didn't mean to. Or if somebody maliciously steals your sensor on purpose and you see that it's flashing green, but that wasn't you, you're not the one who connected it. All you have to do is turn off your sensor, power it down, long press the power button. It'll disconnect from whomever stole your sensor. So that's how to deal with classroom management when connecting sensors. Okay, we are done connecting sensors, so I'm going to click done on SPARKvue. Next, I am going to go to the live data bar down here. So right there, down there in the bottom corner, it says temperature 24.4 degrees Celsius. That is the current ambient air temperature. The lab instructions say to let the sensor sit in the beaker for 30 seconds, come to equilibrium. So we're going to start with water. And the directions say let it come to equilibrium, let it sit there for 30 seconds. You could also just monitor the live data. You can see it drop down to 24.2, but minimum 30 seconds wait to let it come to equilibrium. And then it says, at the same time that you pull the sensor out of the water, hit start. I like to hit start just a fraction before I move the sensor out so I can get a little bit of the baseline temperature in there. And then it says, let data collection go for 1 minute and data collection will automatically stop after 1 minute. So let's see what that means. Start. And then it says, hold the sensor still for that whole entire minute. And I'm trying to make it visible to you. Right now, I'm trying to show you the tip of the stainless steel probe. I can see the drop is hiding itself. There's a drop of water that's stuck right behind the bottom of that probe that makes, you can't see it on the camera, but I can see it looking sideways. But I'm trying to not move because moving can affect the data. So students are directed, hold it still for 1 minute. And you can see that the counter's going here where I hit start. We're only 30 seconds in. We can see that the temperature is dropping, and students might not have predicted that. Students are probably thinking, wait a minute, if that water was sitting there, shouldn't it be the same temperature as the air? Why is it getting cooler? What the heck? And then they can see, oh, it's starting to flatten out. So yeah, it was getting pretty cold pretty fast. So they can start intuitively thinking about slope and rate. And they can think about slope and rate slowing down, like the change in temperature is happening more slowly. And look, it stopped itself after 1 minute. I didn't hit stop. That happened on its own. So after we have the 1 minute of data, students are told to dry off the sensor tip. And I'm just going to set in the next beaker the isopropyl alcohol, since it has to get to equilibrium anyway before we do the next run. Let's look at the analysis tools that students need for this data. Now, look at the graph. We've modeled all of the skills that you want to teach your students about making a graph. So you have title on the graph. You have X and Y axes with increasing from the origin, going up on the Y-axis, going up across the X-axis at regular intervals. And we've got the data taking up most of the space in the graph, but if we want to, we can open up the graph tools and hit the auto scale button and really make the data take up all of the space on the graph. So we've got auto scale. We can also manually scale. So if I want to have a little more control on the scaling, I can hover over either X or Y values and I can click hold, drag down, and manually scale. If I need to do that, I can also move the graph paper around so I can have the origin in a different place if I want by grabbing the back of the graph area and dragging it. And I can completely mess up my data and not know where I'm at and get easily back to the data itself by hitting the auto scale button. So those are different ways to scale. Now, let's do a little bit of analysis. It says that the lab directions say, let's switch to lab directions. Let me bring those directions up from Essential Chemistry. So if you're looking at this lab, this is the teacher version of the lab. Here are lab preparation instructions, the same that you saw in the screenshot a minute ago. Here's the procedure. Oh, sorry, this is the wrong lab. We need 11A. I accidentally had 8D open, so we're going to navigate to lab 11A. There we go, that's the correct lab. Okay, well, so we've completed the procedure step 9. We did step 10 with scaling the graph. Then it says to determine the maximum temperature, minimum temperature, change in temperature, and time for the cooling region on the graph. Record these values in table 2 on your answer sheet. Answer sheet. Okay, so the answer sheets, that's what students write on. They can either fill out a Google slide or form fillable PDF. If you want to turn things in digitally, you can. And we're going to fill out a Google slide in a second, or if you have Google Classroom. Or you can print this out and have students fill out a paper. And if you don't like the way you want to modify the answer sheet in any way, here's the editable version of it in docx form. So let's do what it says. Determine the maximum temperature, minimum temperature, change the temperature, and time for cooling on the graph. We're going to enter all those in the answer sheet. And I showed in part 1 how we can use that Google Doc. You can share it to your students and then make each student a copy and they can fill it out. They're going to just enter the answers they get in the type here sections on the Google Doc. Rather, this is a Google slide, but it functions the same as a Google Doc where you can enter text. So let's get the values that are being requested. We need to get the highest temperature, which looks like it's right there, the lowest temperature, which looks like it's there, and how long would this go on? Well, it was dropping. How long was cooling? Cooling happened the whole time, so that's easy. That's 1 minute. But we can use tools to figure that out as well. So the tool I'm looking at here, I'm pointing at the coordinate tool. If I click it, it puts 1 in the middle of the graph with a gray box that you can grab and drag to whatever point you want, and it gives you the X, Y coordinates. So time of 0 seconds, it was 24.2. That is the maximum temperature. I can fill that out on my form. Maximum temperature for water was 24.2 degrees Celsius. I often get asked, can I change that to Fahrenheit or Kelvins? And yes, you can. If you wanted to change the units, you can. All you do in SPARKvue is you go to a measurement that works either for X or Y, tap the measurement, tap the unit that comes up on the right side, and click the unit that you want, and all things update to the unit that you just changed to. Not only the values on the y-axis change, but also the value for the temperature while the units per second stayed the same. I'm going to go back to Celsius. So yes, you can change units. Okay, and we want the minimum. So let's just put another coordinate tool and drag it to the lowest. And that's 22.7 degrees Celsius. So you get the idea here. I can use the Google Sheet, 22.7 degrees C. It already has the unit there in the table. Now back to SPARKvue. That was just one way to get the minimum maximum temperature, and I'll show you a few different ways that you can do that. Now, the next run, isopropyl alcohol, so it's the same instruction for students. They're going to hit start. Oh, I forgot, I didn't do the rest of the analysis. Let's go see what the directions say to do. It says, oops, wrong button. I meant to hit a tab. There, that's what I meant to do. I had to get maximum temp, which I got, minimum temp. I need the change in temperature. So, okay, so delta is always final minus initial. I can take my 22.7, subtract 24.2. I can do that with the calculator, totally fine. Or let me show you something else I can do. I can tap this initial coordinate that I put on there. And when I tap the bubble, I get these other tools here. See the delta? If I turn on delta, it puts on a second coordinate. And I can drag that coordinate to the final temperature, and it automatically calculates delta Y for me, negative 1.5 degrees Celsius. So it puts the negative because it dropped. It's always final minus initial. And the change in time was 59 seconds. So it was a little bit less than 1 minute, but that's not a problem. So I have a negative 1.5 degrees C change in temperature. So that's what I put here, negative 1.5. And the cooling time, it says to take your change in temperature over the cooling time. So that would be 1.5 degrees Celsius negative. Divide that by 59 seconds. And that is negative 0.025. That's my cooling time. Cooling time is 59 seconds in seconds. So therefore my cooling rate, after I get my divider, I already forgot that number. It was negative 0.025. Go back and add that negative 0.025. Whoops, typos. Typos abound today. Sure that negative sign is in there. That's my rate. So we're going to compare the cooling rate in degrees per second for water versus rubbing alcohol versus nail polish remover. And we are going to get that graph into this document. I'm going to come back to this in a minute to show you how we can put graphs into work digitally. Let me get rid of this calculator and back up there, and let's get back to SPARKvue. Next run. All right, it's the alcohol run. So you hit start and look at the sensor tip. You might not be able to see that in the camera. I still have a drop of water. Oh, look at that rate. Wow, look at SPARKvue. Students see this and they automatically say to themselves, wow, it's going a lot faster, or that's a heck of a lot steeper. So another informal way to think about rate, this is chapter 11. Rates come into play in chapter 14 with reaction rates, especially. So, but this time we see it's flattening out pretty early on. And even the temperature's already going up a little, but I'm looking at the drop. I'm making an observation about the tip of the sensor, and I see, oh, the drop looks like it's getting smaller and smaller a little bit. It's kind of stabilized here. I think it's a little bit smaller. Not quite warming up. It looked like it was warming up at first, but then it went back down. So there was this little trend. But you know what happened right now? The air conditioner just turned on in the room that I'm in, so it's affecting the results a little bit. Not so much, not so terribly. Okay, it stopped itself after 1 minute. So following the directions, we dry the sensor. I'm just going to set it there in the acetone for when it's time to do that next run, so it's already equilibrated. Now, you might be wondering, well, I want to see run 1 at the same time. Where to go? Here's the graph legend, and you can see that I can pick it up and drag it and move it anywhere I want. Run 1 was purple. It's unchecked. If I check it in the legend, it shows up again with the analysis tools that I had on originally. Great. Let's say that now I'm ready to analyze run 2, but wait, what's run 1? What's run 2? Let's put some labels on these runs, because that is another thing we want to teach students, is to communicate as much as we can about our data. So let's name the runs. Run 1 was water. If I go to the experiment tools here on the bottom right in SPARKvue, I can choose manage runs, and down here I can rename run as water. And I can rename run 2 as isopropyl alcohol, IPA. So you get the idea. We can customize and modify to model the types of things you want to see your students doing. So we got water, isopropyl alcohol. Here's a second way to get the minimum and maximum. I want that for the green run, so I'm going to go into the statistics tool. Right here, it's a sigma button under the graph bar. If I can choose minimum and maximum among these other choices, but if I just select those two and say, okay, it'll drop right in the middle and tell me the temperatures with a bunch of extra digits, minimum and maximum value for the entire run. If I want just minimum and maximum for part of the run, I can switch from this hand move select mode. If I click that button, it switches to that rectangle. And if I draw a selection, it will give me the minimum and maximum. Whoops, I accidentally put that in the wrong place. For just whatever data is highlighted in yellow. There it is. Did you see how the numbers are different? Now, if I take off this special selection by touching the green part and hitting the X, now it's giving me the values for the entire run. So you can either do select parts of the data or the whole run. And I'm often asked at this point, hey, can I exclude data points? And the answer is no. The only way you can exclude data points is by doing selection and doing analysis just on the selection of data. Okay, so now students would have to recognize that they have to round to a single digit, just like the live data shows. So 20.3 is the minimum and the maximum is 24.1 for this run. So that was the second way to do the analysis. And finally, the third run, let's say, oops, I forgot on water. Let me see if I can do minimum maximum on water. Okay, so if I go and I do water minimum maximum, that didn't do anything. Because if you look at the legend, the red box, which means the active run, is around the green run. The green run is this run, the isopropyl alcohol. If I want to analyze the purple run, I have to select that in the legend, and suddenly everything becomes active again. Now, when I do my minimum and maximum, that will be applied to the purple run because it's the one that's got the red selection around it. Okay, so that's how you deal with more than one run at a time. You can hide or show runs as you need to. And finally, this lab says now no, do acetone. Same thing for acetone. Okay, so ready, hit start, go, and wow, that is like way steep compared to the other two runs. I can't even see. There's a little bit of a drop of stuff on the end of that sensor. I'm trying to hold still. You can see that I moved. I did affect the data by moving a little bit. And it's going down at a quicker rate. I can barely see. I don't think there's any more liquid left. In fact, look at my data's doing. It's definitely warming up already. There's no more liquid left on my sensor and it's warming up. I wonder if there's something to that. So we're going to hold still and wait for that final 60 seconds to complete, even though all of the data is there. And yes, you can have all three runs shown at the same time when you're live collecting data, so you can compare live during data collection. You can see there's a big difference in the way that the substances behave based on their identity. Acetone, look at it. It didn't even start where it should have. Why did it start so much lower? Okay, the 1 minute's up. So now we can do another analysis. We can change that name to acetone. You get the idea here. And so students would wrap up the investigation by then building the molecules, looking at the pattern of data in SPARKvue, looking at the quantitative data and saying, okay, I see water. It decreased the whole time. I got my rate. My rate was whatever, was pretty low. Then I do the same for alcohol. The cooling time for alcohol, though, was much lower. Cooling time for alcohol. So the time when it started warming up, so where was that minimum of 20.3? Let's find that. Let's use a tool. Now I'm on the green run. Let's use the coordinate tool to find where the temperature was 20.3. And it's not showing up here because I guess it's rounding. So then I'm just going to visually pick that point as the minimum because that looks like where it first hit the lowest. So the cooling time was at 24 seconds. So it went from 0 seconds to 24. I could verify that with Delta tool, but I know that the value is 24 seconds because it's giving me that XY coordinate. So I not only got much cooler, so not only did I get like 4.2 degrees cooler, I would take 4.2 degrees and divide by 24 seconds and I would get a much faster cooling time. If I did the same for isopropyl alcohol, the cooling time is even quicker. Oops, I need to select the correct run first. Here's another way to do analysis that I haven't showed you yet. I can see that that's the minimum temperature right there. If I just tap that point and choose the coordinate tool right then and there, I get the data right there on that point. Exactly, if I just touch it. And so at 22 seconds, it was already at the minimum, and I can calculate the rate that way. And we can see that acetone definitely had the quickest cooling rate, not only visually, but also mathematically. We can we can explain that that was what happened. And we can also say that not only did acetone cool faster, but the temperature dropped much lower down to 17 degrees, where the other runs were in the 20s degrees Celsius. So we can make those comparisons quantitatively. Then we build the molecules, and so students look for patterns in the data. Then they build the molecules going from going to the symbolic here. Now we've got a water molecule, we've got the isopropyl alcohol molecule, we've got acetone. We see similarities. We see oxygen in all of them. We see hydrogens in all of them. We see that the outlier acetone has a double bond. And by the way, the molecular model set lets you do two types of visualizations of molecules. You can just do the ball and stick model, or if you use the small bonds, you can get the spherical structure, the three-dimensional shape that way. And another type of bond you get in the set is a purple bond, which students can use to indicate that's ionic so that if they do something with solubility in solutions and they're building models, they know that if this goes into water, it's purple, it breaks if it's soluble. And that happens in the purple bonds. And that's something you can have them do. Now, going back to this, we see the pattern is we see hydrogens and oxygens across all of them. This one doesn't have any carbons, so we're going to ignore the carbons. But we can look at these two and say, well, the carbons look similar. We've got 3 carbons. These two substances, I see that water's got OH here, OH here. I see that isopropyl alcohol has OH bond here, and acetone has no OH bond. Maybe that's why acetone evaporated so much more easily. It took less energy for the acetone particles to be able to get enough energy, absorb energy from the system, from the surroundings rather, to go into the system and allow evaporation with lower energy just from the existing energy in the atmosphere. Now, what about the isopropyl alcohol? Yeah, it did that as well. Not as well as acetone, but it did not, it took a lot less time to evaporate compared to water. So I see I have a OH bond here. Alcohol particles are a little bit more attracted to each other. They are attracted to each other compared to acetone a lot more. So because the particle attraction was greater due to these, these intermolecular forces, this evaporated more quickly than water, but not as fast as acetone. Whereas water, with every molecule having a number of spots where you can have hydrogen bonding, we've got a lot more particle attraction between particles, and it takes a lot more energy to overcome those particle attractions to go to the vapor phase. So now you've seen complete lesson 11.1, where students started with reading a couple pages in the book. They played around with the simulation. They did the qualitative examination to, if they don't already have experience, get some experience qualitatively, then do the quantitative analysis with data, then model. So we're getting information on all these levels of understanding and all these visualizations and experiences to really learn the concept. And that's what essential chemistry labs and curriculum can help you do. So SPARKvue software. We're going to do more in SPARKvue. I'm going to close out of here. But before I close out of here, here's a way to share data files. If you or your students want to share this file data with somebody else, there's a number of ways. First of all, you can go to the hamburger menu and go to Save or Save As. Depending on your system, you might have different options. I'm on a Windows computer, so I'm just going to do a Save As. So I can name it 11A Data Barb. So I'm saving it to my desktop so I can easily find it later. And if I save it and close it, I can always come back to it later. I can send as an attachment in an email to another student. I could share with my phone. I can upload it to the learning management system, like your Canvas or your Blackboard or your Schoology. And once you have that file, let me show you 2 ways to get there. If I'm in a Windows system, I can just go through the files manager, and that was on my desktop, and I can just find that file and double click and open it on my Windows system. Actually, didn't want to open because I kind of already have something going on here in SPARKvue. So let me close out of SPARKvue to make this work. Now the SPARKvue is closed. Now that if I double click it, it'll pop open in SPARKvue. There's the exact, everything as I left it is still on there as I saved it. So that's a way to save files and share with other students, or save for later analysis if you don't have time and maybe you have to do the analysis on the second day of the lab. The other way to get to that file is through SPARKvue itself. Now, this is what I was showing you before. Go to the hamburger menu and go to Open and navigate to wherever it is that you saved your file and then say Open. That's the second way to get to open that file. All right, let me close out of SPARKvue here. It always asks you if you want to save before you leave. So most of the rest of the day today, I'm going to say, no, I don't want to save it. Okay, so minimize that. Next, here, let me quickly talk about the equipment kit. So you see one of the sensors here, that is the wireless temperature sensor right here. This is the standard equipment kit where you get 6 sensors: temperature, pH, conductivity, colorimeter and turbidity, pressure, and voltage. I don't have time to show all of these, but I will show pressure, conductivity, and pH also, in addition to the temp that I just showed. This kit also has a molecular model set that you just saw, a periodic table, cases to hold everything, This is a distiller, or rather a condenser, so you can do distillation and organic chemistry. This part goes on a rod stand so that you can put in on the end here, you can put in either pH or conductivity sensor. On this smaller hole, you can put in a temperature sensor, and then on the edges, you can put the wires for the voltage sensor. So this helps you do like a titration setup, or maybe you're doing an electrical chemical cell, and it helps you with wire management and electrode management. So this is just a really handy piece to keep organized. And these cards here go along with these two labs or dry labs that are looking for patterns. One of them is looking for figuring out what element is there with the spectrograms, and the other set is figuring out patterns on the periodic table when learning about patterns on the periodic table. Now, the other equipment kits, you might start with this one. It's only got 3 sensors: pressure, temperature, and pH. This allows you to do some, but not all of the sensor-based labs in the lab manual. And it comes also with the molecular model set, the periodic table, and the cards. And then if you want to add on, there's those other 3 sensors we talked about previously, but this kit contains a drop counter. You'll see in PASCO Academy in the titration, we use a drop counter because it just makes titration that much faster and easier. You can do titration in 2 or 3 minutes. 2 or 3 minutes per run flat. That's that. It counts drops as volume for you. It keeps track of volume by counting drops of liquid. So those are the sets of equipment. If you want SPARKvue software, the free way to get it is by going to the App Store for your mobile device. Or if you've already paid, if you're a paid subscriber to PASCO Portal, it's on the portal that you can download. Or if you're an ebook subscriber, you've got the license for 5 years or whatever. You just go to education.pasco.com, where you also get your ebooks. You can download the software from there. You'll see that in part 1. I'll point that out on that website in part 1 of the webinar series. So if you have a phone, it's free. Just go to your app store to get it. There's also a browser-based version that works only in Chrome and Edge browsers. How do you get there? I'll actually demonstrate this in a minute. You go to the website sparkvue.pasco.com, and it works very similarly to the app that you saw me just use, and I will use it later on today. So I'm going to drop that link in chat. That could take you to that, and also instructions on that I just gave on how to get SPARKvue software. But also, how do you get help with SPARKvue? There's how do you get help with the PWA version of SPARKvue? There's a specific link that I dropped into chat that kind of goes over the differences and how do I do the things I know how to do in SPARKvue in the app version? How do I do that in the browser version? So let's now look at, let me re-emphasize that if you're doing an essential chemistry lab, you're going to use the Open PASCO experiment path to get to the pre-built lab. Let's repeat that again with investigation 8D, determining limiting reactants. So I'm going to open up SPARKvue. I go to Open PASCO experiment path. I go to chemistry, and then I find lab. It says do 8D, determining limiting reactants. And we say, okay, that's nice because this lab has a little bit more complicated setup. It's got this graph of pressure versus time. And not only that, but there's a second page required, and students are told go to the second page in SPARKvue. Here's how you do that. You go to the arrow up here at the very top by the title, go to page 2, and here's page 2. It's already set up, but you're going to have to enter some things in the table to make the graph populate. And I'm going to go back to page 1 where we started. Now that's how you get the lab open. Well, I am going to demonstrate something called shared sessions right now. So I'm going to actually have to open a file that I've kind of set up in advance. So I'm going to come back to SPARKvue in a second. And now I'm going to do what's called a shared session. So here's another way to share data and labs with students. So I'm going to go to the main menu, and I'm going to go to shared session. And I'm going to be the person who's sharing the data. That can be anybody. It can be a teacher. It can be a student. And now I'm going to switch my camera to a Spark LX-i2. So here's a handheld device that we sell that already has SPARKvue on it, and in addition to like our other software, everything but we've got spectrometry on here and Matchgraph as well. So what I'm going to do is this device, the Spark LXi, that's going to represent somebody who wants to see my data. And The larger screen, that's me as the person who's sharing the data. So I'm going to do start a shared session. That's something I'm doing. And my name, I'll be the teacher. I'll be Miss P. And I'm going to call the session name something that's easy to spell and remember, DOG, dog, all lowercase, dog. And that's all I need to put in here to be able to share my screen with you. So I'm going to say, okay. Now, if you have SPARKvue, what you can do, and if you have SPARKvue on your own device, you go to the same place, you go to the menu, and you go to shared session, but you're trying to connect to my dog session here. So you're going to choose the top option, manually connect. Let me go back. Um, cancel that. Oops, wrong thing. You're going to go to manually connect to a open session. So again, from the main menu, it's going to be shared session. You will choose manually connect to an open session. I'm just going to call this LXI2. And I have to remember that the session name was dog, D-O-G, all lowercase. So if you have SPARKvue on your device, go ahead and do this. Go to manually connect to a shared session, manually connect to a session, put your name in. The session name is dog, D-O-G, and then say okay. And so this screen says, so I'm trying to connect. Up here in my SPARKvue on the person who's trying to share, it says we've got the LXI2, and we also have Dr. John, and I'll approve you because those look like legit names, not new, students trying to make me blush or anything. So you should see on your screen, that just happened on the LXI2, you should now see, hey, there's that same screen that I'm sharing. And oh, look, I have control. There's a dot moving on your screen. I've got control over your SPARKvue, but you're looking at what I'm looking at, right? So if I want to, I could kick out anybody that doesn't belong there. If I need to do that, I can. But here's what happens if you are sharing your screen. So I'm going to switch away from my screen since you may or may not have one to look at. I'm going to switch away and go to the setup, and I'm going to quickly swap out to a different lab, and we were going to do lab 8D. That was determining limiting reactants. This is one of our most popular labs. It's a stoichiometry lab, and I'll quickly explain what we do there in a second. So in this lab, we get the same volume for 5 runs, 40 milliliters of 0.12 molar baking soda solution or sodium bicarbonate. So 40 mils for run 1 of 0.12 molar baking soda solution. We're going to add 0.1 grams of citric acid. Those two will react. It's an acid-base reaction of weak acid, weak base. We're going to get carbon dioxide produced. We're going to stopper the bottle and collect the carbon dioxide product in the bottle and also connect a pressure sensor to, let me zoom out on my camera a little bit so you can see that a little bit better. There we go. So we're going to capture the pressure due to the change in CO2 gas in the bottle, and that'll give us an idea of how much product is made when we have 0.1 grams. Then we're going to do a second run with the same volume and same concentration of baking soda, but then we're going to do 0.2 grams. We're going to double it and see what that does to pressure. Then we're going to triple the mass of citric acid. We're going to keep varying the citric acid, but keep everything else the same and see the effect, because eventually we're going to figure out visually what is the ideal ratio. And unless it's ideal, then there's an excess and there's a limiting. So we're going to look at all the runs and identify limiting reactant, excess reactant, and ideal ratio. Now, this is a 500 milliliter plastic Nalgene bottle. I love using these. They're easy. You can also use a 500 milliliter Erlenmeyer flask, or go to the grocery store, get a Powerade bottle. This is close to 500 milliliters. This is Powerade, and number 6 one-hole stopper fits, which means you can do this with it. This works just almost as well. It's a slightly larger volume, so you get slightly lower pressures, but the proportions still work. So that's an easy way to do that. And by the way, the stopper does come with the equipment kit. So does all the things you need to make the pressure sensor work with this. They all come included. So let's get started with that first run. Now, if you are connected on a connected session, you're going to see the data populate on your graph at the same time as mine does. So the directions say, well, we have to connect that sensor. So I'm going to go to the Bluetooth icon. I'm going to turn on the pressure sensor. And there it is. Tap to connect. Wait for it to connect. And then say done. And now we have a pressure down here, 101.8 kPa. Uh, so usually I've got a lab partner, and my lab partner would help me hit start. So I'm going to kind of move my mouse over, prepare it now. So I'm going to put in the 0.1 grams, drop it in, quickly close it, but I'm going to hit start slightly before I do that so I can get the baseline pressure. Start. Drop in the sample, seal it. I'm holding the bottle at the top like this to kind of hold that stopper on while I'm mixing. And I'm trying to always use the same motion when I'm mixing, and students are told all these things in that lab procedure. Gently swirl, and you can see the graph is populating with that pressure data. And I'm going to on purpose mess up my data to show you how sensitive the equipment is. So if I squeeze the bottle, this is why I'm not holding it down there, because that sensor will pick up that change in volume just by squeezing the container. Don't worry about this, not going to affect our analysis. I can also be looking at the data. If I've done something wrong in experimental setup and I don't see an increase in pressure, or I see pressure decreasing, maybe I've got a leak in my system and I need to tell the teacher. So you can help students with what to look for. Also the graph also helps you see whether or not it's leveling off. I'm going to quickly switch my screen to show what's happening if you don't have a live connection, you can see that anyone who is in a shared session will get the same live data that we're looking at now, but eventually when I stop the shared session, they get to keep that file and they get to do the analysis on their own. So they get to use the coordinate tool. They get to use all those tools I showed a minute ago. And for time's sake, I'm going to hit stop because, yeah, I could maybe let it run another minute before it really levels off, but I'm just going to hit stop because I'm running low on time. So I take the stopper off. And now at this point, I'm going to show you that I actually pre-did all 5 runs. I really just wanted to show you what how this lab is set up. So I'm going to kick you out of the live session. Let me go back to the camera showing the live session. I'm going to kick you out of this. I'm going to stop the session for everybody and watch what happens. Okay, so the thing went away, the connected session went away, and anyone who had connected to my session now has the file and they can do their own analysis as needed. They can do anything they want to this file as if they collected the data themselves. Now it's yours. So that's called the shared session, and that's another way to share files with students, not only within the classroom, but anywhere in North America. The last time we did this, there were people from all over the United States and Canada who at the same time were all doing this lab together. It was wonderful. So now that's your file. You can save it. You can do analysis. You can do whatever you need to do on your file. So now I'm going to ask you, now that you have this cool data, I'm going to ask you to please push it aside because I want to show you some more things on SPARKvue. Now, please look at your Zoom. Okay. So I stopped that run early because a long time ago I got run 1 and it's already here in the graph. So here's run 1. Okay, run 1. Whoops. I'm getting ahead of myself here. So on run 1, let's do the analysis. I'm going to show you, let's get the coordinate tool. How about that? I need the initial pressure and the final pressure. So I'm going to use 2 coordinates and I could subtract. Now I could do that like I showed you by coordinates, but I'm going to go the easy way with delta. So maybe you show your students this after they've done plenty of subtractions to get delta. The change in pressure was 5.3 kilopascals. So the instructions tell students go to page 2 and enter 5.3 kilopascals. But actually, when I went and I got my mass of citric acid, I didn't have exactly 0.10. I had 0.11 grams, 0.11. So if I enter that in SPARKvue, it will plot. There's my data point here. It plotted that XY pair. So when I go get my second mass of citric acid, maybe I got 0.20 perfectly. Great, I can leave it alone. If I need to edit it, I can. Let's look at what happens when you do 0.2 grams. Look, the pressure just about doubled. And if we do the analysis, switch the pink run, do the analysis here, we can get the delta, and we've got 10.3 kPa. That's just about double. So enter that, 10.3 kPa. Wow, we doubled the mass of citric acid. We got double the pressure. I bet you if we triple the mass, we'll get triple the pressure. And indeed we do. What if we quadruple the mass of citric acid? Oh, we did not get 4 times the pressure. Something's going on. 5 times. We didn't get 5 times the pressure. And in fact, this something happened here with my data. Let me scale out and see what happened here. Let me close some of these analysis tools so it's easier for you to see what's going on. Let me go back to the blue run and turn off the tool. You just have to pick the tool and hit the X. So on run 5, the stopper actually popped off. And how did I get that note on there? There's this annotation tool, this letter T. If you touch it, you can enter a note. I spelled stopper wrong, but you get the idea. And you can move that note to anywhere you need to on the data, either point by point or by grabbing the gray box and putting it where it's needed. So that's how I got the stopper popped off note on there. So we can see visually, without doing any math, that students can qualitatively see by run 3, we've hit that ideal ratio. We keep adding more and more mass of citric acid, but we're really not getting more and more pressure change. So the product is kind of leveled off there. By run 3, we've got a ideal ratio. So you can end the lab there if you want to stick with qualitative, but you can even take it further and do the quantitative as it's written. It's written to have students do the quantitative analysis where they take the grams and convert to moles, and then they divide moles by moles of citric acid to baking soda. And they figure out that at run 3, where we can see everything's leveled off, at run 3, we've got the ideal ratio. And that means that in the first run, it was not the ideal ratio. So there was something that ran out and there was something that was excess. It had to be the baking soda that was excess and the citric acid that was limiting, because when we added more citric acid in the next run using the same amount of baking soda, we got more CO2 produced. So in the first 2 runs, citric acid is limiting, baking soda is excess, and run 3, neither reactant is limiting or excess because it was the perfect ratio, since we didn't really see much change in pressure results for the next 2 runs. But then this also helps students think of nothing's permanent. If you keep changing the conditions, then we're going to get change in outcome. So then after run 4 and 5, students should realize, oh, suddenly citric acid is now the limiting reactant. I'm sorry, the limiting run. Nope, excess. Citric acid used to be limiting in run 1 and 2, but in run 4 and 5, citric acid is excess because I'm adding more citric acid, adding more, it's not all reacting, it runs out. So now it is the limiting. Wow, keep saying that. It is now the excess. We're adding more and it's not reacting to produce more gas. That means baking soda is running out, and baking soda is limiting now in the last 2 runs. So we've flip-flopped identities after the ideal ratio, and students can get all that either by doing math or by visually seeing it and stopping there to see that run 3 is the ideal proportion of reactants. Now, you might be wondering, how do I get this? How do students get this graph in their lab report? Well, A, they can hand draw it. They can. B, they can do a screenshot, which is what I recommend, and the easiest thing. So I'm on a Windows machine, and the screenshot shortcut to do a specific screenshot is the Windows key Shift S. And in a moment, I'll share a slide with you that has kind of the shortcuts on it. And I select which parts that I want of that graph. And then now that I have it on my clipboard, I can go to the lab write-up. I have a different one open here. Let me open up the, well, let's just use this one. So I know this is lab 11A's graph, but the instruction sheet tells you there's 2 ways you can get the graph on here. You can either copy and paste it, or you can draw on the graph that's there. So the directions tell you what to do. They say go to the squiggle tool by going to the line, selecting scribble. And now you can draw directly on here. So that means you're going to have to delete this. I have to turn this off first before I can do that. So delete the directions. You can type in the numbers for the X and Y axis. You can type in what you need on the legend, and then you can turn on the squiggle tool, and you can draw on the graph using Google Tools. And then you can draw the other runs. So I'm exaggerating my drawing here, but that's just one way to get your graph on an answer sheet. Another way is to paste in that graph that you copied using the shortcut, and you can resize it like that. You can get rid of the legend, since it's already on the SPARKvue graph. So I think copying, pasting, and putting into a Google Doc or a another document like a Word doc is probably the easiest way to get a graph into a lab report, or print it out. Just your Control P to use a system printer to print it out the old-fashioned way. So that's how to get graphs out. Let me go back to the presentation. There it is. So we went over shared session. How do we get there? We first went to the menu, the hamburger menu. We chose shared session. If you are starting the shared session, that's on the right side here. Oh, sorry. You would hit the start shared session if you're the one who's sharing their data. If you're joining a session, you are going to click manually connect and say done. You put in your name and the session name and then say okay. There is a cheat sheet in your resource folder that explains all the steps we just went through. So more ways to share and save data. I showed you saving this file, opening, closing, and it's just like a normal file that you trade and share with somebody. You can take a screenshot. So I told you I had Windows. I use the window key Shift S. If you're on a Mac OS, you're going to use the, oh, I can't ever remember the name of that button. Command Shift 4 to do the screenshot. If you're on a Chromebook, which uses the Chrome OS, you're going to use Shift, Control, and that key at the top of the keyboard. If you ever wondered what that was for, that's for screenshotting. Shift, Control, that key at the top and kind of in the middle of your keyboard at the top there, and to take a screenshot where you can select the area of a screenshot. Finally, you can also export your data from SPARKvue to another spreadsheet program. Believe it or not, SPARKvue is incredibly packed with analysis tools. You'll be surprised at how much we've packed in there. But if you're used to, or if you want your students to become more used to using Excel, you can export data from SPARKvue so they can use it in Excel. All you do is you go up to the hamburger menu and you choose export data. And you save it with whatever file name, and it will save it as a CSV file. And there, okay. And I'm saving that to my desktop so that I can open that either in Excel, or I can bring it into Google Sheets or whatever other program accepts CSV. And that is another way to share data. Now, so those are the top ways to share, move and share SPARKvue. There is a resource in your folder, like I said, that what's incredibly packed with tools in here. You will be surprised at how much we've gotten here. Just go to that SPARKvue quick reference in your resource folder. We haven't even scratched the surface today. It would take days to teach all of this. How do you get help if you're ever stuck in SPARKvue? Well, there's the help, the SPARKvue help. So actually it's this link here, this SPARKvue help link is actually embedded in the program. I'm going to put it in the chat. But you can go to that link directly in a browser. But what you probably want to do is you're in SPARKvue, you're like, I can't remember how to do linear fit. We'll do linear fit next. So you go up to the hamburger menu up there and you go to help. And if you choose help, it'll take you to that website I just gave you a screenshot of. Easiest thing to do is go to the top right in the search bar, type in the thing you're trying to do, linear fit. There it is. Fit aligned to data. There's screenshots and lots of explanation here, tips, and related components, and also the table of contents here to help you get the help that you need. So not only do we have a built-in help system, but we also have, I'm going to paste in the chat here. If you go to our website, pasco.com/support, you can get a hold during PASCO hours during Pacific time. I believe it's 7 a.m. to 4 p.m. Pacific. Might have to double check that, but you can chat with our teacher support agents, or you can give them a call, and they're there to help you. So there's that for help. Now I'm going to show you how to use SPARKvue in the progressive web app. Like I said, there's a browser-based version of this SPARKvue, so I'm closing the app. And now I'm going to go to a browser. So I'm opening a browser and I'm going to go to sparkvue.pasco.com. That's a website, which I have previously pasted in the browser. It's in there. It's just sparkvue.pasco.com. And look at that. I'm in a Chrome browser and I'm using SPARKvue and it's free. However, it's working on your desktop computers and your Chromebooks. So on phones, just go to the App Store and use the app. Otherwise, you can use this browser on Chrome and Chrome and Mac OS. Or not, sorry, I just lost my train of thought. Chrome, Mac, or Windows OS with Google Chrome or Edge browser. So I am going to now do experiment. Which one was it? Let's see, I forgot the number. It is 12B, Boyle's Law. So we're going to do a different kind of lab here. We're going to do some mathematical modeling. Here's a little bit of advanced peek at what SPARKvue can do. So we wanted to look at 12B Boyle's Law. Open, remember that path, open PASCO experiments, essential chemistry, scroll down to 12B Boyle's Law. Okay, so here's the gas laws. Now I need to connect my pressure sensor. I'm going to switch to the lab setup. I don't need the bottle anymore. So this lab just calls for two pieces of equipment, which again, both are included here. The syringe, which it says to start at the volume of 30 milliliters volume. So we got to connect the pressure sensor to SPARKvue. We're going up. Again, we're in a browser here. So notice the first thing that's different. I hit the Bluetooth icon and my devices are not coming up. So in the browser version, you hit Bluetooth twice. You got to hit Bluetooth again. And now there's my devices. Okay, so I can tap my pressure sensor to pair it. It means connect. This is kind of Google's Google's control here since it's a Google browser or Chrome browser. And now my pressure sensor is connected. Look, that looks just like you saw before. Same options as before. I can disconnect and I can double check my 6-digit code to see that I have the right one. So I say done and I'm good to go. I've got my live data. Now I know I'm definitely connected, but then I have something called manual here. So when I hit start, it doesn't just collect a bunch of data for me. It gives me the live data, but it's not plotting anything because I haven't told it to plot it. I have to tell it with a check mark to keep the data point when I'm in manual sampling mode. So the directions say set the syringe to 30, and we're going to vary the volume and see how the pressure responds. Then we're going to fit a mathematical model to see if we can figure out Boyle's law. All right, so we're starting at 30 for volume, but my table says go from 60 down to 15 milliliters. So I'm going to have to do this one-handed. This is really difficult to do for someone with tiny hands like myself, but I can do it. Normally you'd have a lab partner helping. So I'm now at 60 milliliters. I'm going to let the pressure stabilize and the temperature too, and I click OK when it looks stable. Then I go down and let it go down to 55. Let's see, is that 55? There it is. 55 right there. Stabilize. Boom. I kept that value. Notice that when I record a value, it turns black. So if I have a colored value, it means it's not recorded yet. So I got to make sure I get them all. Now let me go down to 50. Look what pressure is doing. It's going up. Okay, pressure's going up. The volume's going down. That's interesting. I already see a relationship, but I'm going to fit a mathematical model so that I can make predictions. Like, why do we do modeling in the first place? It's if we have a well-fitting mathematical model, we can use the equation to make predictions about future, like, climate modeling. Something very hard-hitting for all of us. There, 35 milliliters, 30, back to where we started. 25 milliliters. This is where it gets really tough for me. And students will notice, oh, this is getting harder to do. Okay, 20 milliliters. I can barely hold it steady, so you can see I have a lot of moving on my numbers. I'm trying to be still here. Okay, and then 15. Oh my gosh, it hurts. Like I said, you should be doing this two-handed, but hey, I don't have a lab partner today, so. There. Okay, not bad. So now I've got my last volume measurement. I have a black value here. It's recorded. I can hit stop. Let's say I messed up my volume measurement at 30. I can always just click it. As long as I haven't hit stopped, I can go back and correct a value. And I can retake my volume at 30. If I need to, there it kept it. And I have all the values that I need and I hit stop. And now I've got all my data points. I'm going to scale my graph. And we see that, let me move that out of the way so you can see a little bit better. You can see that there's definitely a trend. There's a pattern here, and students might right away recognize that. Oh, that's not linear. Well, it's not a straight line anyway. It's a curve. So this probably I'm probably not going to need a line best to fit straight line, but I can probably fit some kind of curve line. So using the graph tools here, yeah, like you can stop the lab here, and students can recognize, oh, when I have this shape, it's an inverse fit, right? As one goes up, the other goes down. You can stop the lab there and leave it at that, or you can take it all the way as it's written to mathematical modeling. First step in mathematical modeling, look at the data. Do you see a pattern in the data? If I change my volume from 60 to 30, that means cut it in half. What happens to my pressure? Pressure's about 52. When I cut volume in half, oh, it just about doubles. Volume in half, pressure goes up double. So I've got this. Okay, I've got the opposite trend. What if I um, multiply my volume of 60 by 52? What number do I get? What if I multiply my volume 20 by 150.8? What number do I get? Okay, so that's another way to look for patterns is multiply these together. Or what if I take 60 and divide by 52? What number do I get? What if I take 15 and divide by 195? What they're looking for here, is there a constant of proportionality? Is there a constant? If I do some kind of math, divide, multiply, some kind of pattern here. Okay, so that's one way to do a little bit of modeling, but you can do curve fits to get an equation out of your data. So there are two buttons here that will do fits. The first one is a linear fit straight line. Let's see if that works. No, it's not a linear fit, doesn't fit the data. So the predicted line shows up on the graph and shows you not only the fit, but also gives you the parameters so you can evaluate the fit. Hey, look at my R value. It's really close to -1. However, I can also visually analyze and see, oh, that doesn't overlap the data really well. The data is not really bunched close to that predicted line. So even though my R value, well, it's not super close to negative, when that 0.9 looks like it's okay, but you can do better than that. And we could tell visually it's not really a good fit. So we go to the next options, the curve fit. So this was linear fit, and then there's curve fit. I'm opening up curve fits. Linear fit is an option there, and it shows you the prediction of if you use that fit, here's what it looks like. That doesn't look like my data. Let's try quadratic fit. Nope, that doesn't look like my data. Power fit does not look like my data. My data sort of looks like inverse fit. My data sort of looks like inverse square, even though I have something over here. I do have this shape. Sine, nope. Gaussian, nope. Cosine, nope. Natural exponent, well, kind of. It's reverse though. Natural log, nope. So it's one of these, inverse or inverse square. And it gives me the equation. Here's my mathematical model right there. There it is. So let's determine which fit is better, inverse or inverse square. Let's try inverse and we say, okay, wow, look at that. That's a nice fit. Not only does that line overlap the data really well, and I can also look at the mean square error and the root mean square error to evaluate the fit. In this inverse fit, mean square error, that's going to have units that are squared, which is, I mean, it's the number's useful, but root mean square error is kind of a better uh, way to evaluate. You want them both close to 0, and they are pretty close to 0, but root mean square error will give you the value that the predicted value will change plus or minus around the curve compared to the actual data values, but in the correct units. So if you want, another thing you can do here is you can go to the gear icon on the graph and say, you know what, I really don't want to see the connected lines on the graph. I want to see just the prediction line, so I can turn off connected lines. And what that does is it turned off those data point connectors that were there before you did any kind of analysis. And now we see only the fit. And we can see how, oh, look how close those lines are to that predicted model. Wow, that's cool. But wait, we still have another model we can try. Let's try that inverse square. Not as good of a fit. Okay, so now we know the equation is this: y equals ax plus b, a over x plus b. What is y? Y, well, that's pressure. It's on the y-axis. Y is the thing on the y-axis. What's x? Well, what's on the x-axis? That's volume. Okay, so on this equation, y equals ax plus b, a over x plus b, y is pressure, x is volume, a is a constant of proportionality, which it turns out if you multiply these, or rather if you multiply the numbers, you get that constant. It's about 2,900 in this case with this data. Plus b is the y-intercept. But let's use a little bit of logic here. If we look at the x-axis, we would see where would we hit on the x value of 0? Where does that hit y? But if we think about what's on x here, volume, There's no such thing as zero volume. It doesn't exist. Zero volume can't exist. So that means there's no such thing as a y-intercept. That means I could totally cancel out that plus b from my formula. And now my equation is y equals a over x. Okay, cool. Well, what do I do with that? Well, I can predict either the pressure or the volume at another pressure or volume given with the proportionality constant A, which is given as 2900. So let me turn on my tool here, my annotations on um, Zoom. So that means y equals a over x. Sorry about my terrible writing here. What if I don't have a data point for a pressure of 160, but what if I want to know what would the volume be at pressure of 160 kPa? So that's my y value. I can plug that in for y. I'm trying to find out the volume. And for a, my proportionality constant, it's like a slope, changing one over changing the other. I can plug that 2900 in for a, and I can figure out that volume. So this is what mathematical modeling is all about. It's finding the equation that fits the data. And if it's a really good fit, which you can evaluate in this case using mean square and root mean square error, if it's a really good fit, we can make predictions about either variable. So we're looking for the equation that relates the two variables to make predictions. And this is what science is all about, people, right? We really want students to do this kind of stuff. So do try to share this stuff with your students. It's there in SPARKvue and more. All right, I know I'm coming up on 90 minutes here. I got kind of a late start, so I apologize for that, but I am going to continue. If you need to leave, go ahead and leave. Don't worry, I'll send you the recording and I'll get through all of the, I'll keep recording. But if you need to go, I understand, go ahead. Okay, thanks for attending. So I'm gonna continue here. So we did some manual sampling in the browser-based version of the app, so this is free too. All right, so you can do all the same things too. You can save it, you can export the data, you can do shared session, all that good stuff. Still works here in the browser version. So I'm going to leave. And a summary of all that stuff I talked about with the equation is right here. Remember the y-intercept, that's where the y-axis value where x would equal 0, but remember we can't use zero volume, doesn't exist, and that's why we rearrange the equation to yx equals a. Actually, I did a little bit of algebra here and I moved the x over to y by multiplying. And that is Boyle's law. Y1, x1 equals y2, x2, or P1, V1 equals P2, V2, right? That's the math equation. That is Boyle's law. This is what Boyle is most famous for, I would argue. And here's how you assess the fit. You look at the mean square error and the root mean square error. And they each do tell you about how different is the data from the predicted line, and they're both a measure of the goodness or the fit of whatever model you picked for your data. And you want them to be close to 0. Now, another use of curve fitting this data, and I'm not going to do this lab because we don't have time, but you can find it in PASCO Academy. This is Academy topic number 18. Go into Academy. Let me do a quick run into there. So here we are. I'm on the teacher version of education.pasco.com. I've got my code already punched in. And if I click Academy right here, here are all the Chemistry Academy topics. I said it was topic 18, solutions, view the topic. Here is the teacher prep that explains the lab. Here's the student data collection that you can share with students. And here's the follow-up video for students and all the files that you can share with students. Now, one of the files that students will get is a SPARKvue file. So you know how, like I showed you that when you share, when you can save a file and you reopen it, it has all the data there. And if you did any analysis, it's there. We share that file of data we collected from the video. So when students watch a video and they open a file, it's the same data they saw us collected in the video. It's the same file. So students can do this particular lab, this electrolytes lab. It also uses curve fitting, but in this is a little bit easier for students to understand when it's a linear fit. It's a little more intuitive. So let me real quick open that data and show how the linear fit model works. So here's already collected data. What they do is they collect 5 or 6 different concentrations of NaCl solution, and they see that the conductivity increases as the concentration increases. It's kind of like Beer's law. If you ever did the Beer's law with spectrometer or colorimeter, we do have a lab for the colorimeter with Beer's law, but this is the same concept. You get a series of known solutions. You fit the data. You determine that a linear fit is the best fit. You use that equation, y equals mx plus b. Students totally know this formula from their math class. It's so fun to show them how it works in science, how you can use this to make predictions, just like we did with Boyle's law with the inverse fit. We could do that with linear fit too. But this time we can use the y-intercept b because concentration can be 0, and we do have a 0 value for that. Look at my fit on a linear fit. I can assess the fit with R. On a linear fit, you want an R as close to +1 or -1 as you can. It's -1 if it's decreasing. It's +1 if it's increasing. And we have an increasing. It's a perfect R equals 1. This is a very good fit for the data. So what can we do with this? Well, we can take this linear fit and we can get a Gatorade, a sports drink, and take the conductivity of it and figure out the concentration of ions in that solution of Gatorade based on whatever conductivity it reads. We can plug in the conductivity for Y. We plug in the slope M. We solve for X, and we plug in the value 172 for B. So it's, hey, this is how we figure out the concentration of a drink if we're doing some quality analysis at a factory, for example. So that's this is lab 13 A, which is topic 18 in PASCO Academy. The linear fit equation is similar. You've got the xy values on the graph. M is slope, which is the rate of change. And then B is the y-intercept, where the y value where x is 0. Here's a summary of how to interpret the R and root mean square error. Root mean square error, it's going to, how big is the error? You want it close to 0. Also, how much far away are the data points from the best fit line? Okay. Now, some tips on conductivity and pH sensor. I'm going to swap out my equipment here, so bear with me real quick. I'm going to change from tray of nothing to a tray of pH. And I can tell you right now that, well, we're not going to have time to do experiment 3C, but what you can do is you can go to PASCO Academy and you can find experiment 3C. It is the topic 3, classifying matter, review topic for physical or chemical change. Look at student data collection. Roger and I do a little intro. It's just some fun stuff. And then we jump in and start doing the lab 3C. So you can see it done here. All right, since I don't have time to go over it now. Okay, so conductivity and pH sensor use tips. Now the pH sensor, I always get lots of questions about this sensor. How do I take care of it? What do I do if the solution runs out? How do I calibrate it? Do I need to calibrate it, etc.? I'll get to those questions. So first, the basic use. So it comes with a cap with storage solution. When time to use the sensor, you have to take off the storage solution bottle. And when you do that, you can see that students are right away going to knock this over and spill the solution, right? It happens to me all the time. So it says right on the bottle what the solution is. It's 4 molar potassium chloride. However, that is buffered at pH 4. So if you're going to make this yourself, you can buy it from PASCO. You get a giant 500 milliliter bottle, which is enough for years of refilling. Or you can make it yourself. You get buffered pH 4 solution instead of just distilled water. You never want just distilled water in here. So pH 4 buffered liquid, and make it into a 4 molar potassium chloride solution. I have the recipe on a different slide. That's all that the storage solution is. Make sure it's clean, fill it up about this much so that when it's on and screwed onto the cap, that it's covering the glass bulb on the pH sensor. Now, when you're ready to use the pH sensor, you're going to want to handle it by the blue plastic. Don't try and be twisting like this. That might damage it. You want to handle like this. Take off the cap or push it up. In this case, we didn't use test tubes, so I'm going to gently twist without squeezing. There, and I got the cap off. And we're going to always rinse, swish, rinse, and pat or shake dry. So here's what I mean by that. Now, everybody's used to doing this part where I have this beaker of water here. This is just tap water on this beaker here. I just didn't want it to evaporate. That's why it was closed. So I'm going to rinse the probe with distilled water from a squirt bottle. Swish. Rinse again. And either shake dry or pat dry with a lint-free, scratch-free wipe. You don't want to damage the glass electrode. Now, why did I do this extra step here? That's because the sensor has these fingers. It's kind of hard to see there, but there's these fingers where it might be really easy to trap solution. So if you rinse it a little bit first and then really swish it in some tap water and rinse it again with distilled water, you're definitely going to remove anything that might be stuck in there and you'll get good results. Okay, so that's the directions, and that works not only for pH sensor, but also conductivity. It's the same thing here. We've got some places where the electrodes are where it could easily get stuck. So now more here's a thing that you might be used to if you're used to using SPARKvue. You might be used to using the sensor data path. Now, that is a fine path to use. It doesn't work for that well for essential chemistry labs, but if you want to just do a random test, or you're doing, there's this assignment in chapter 16, section 2 in the ebook, and it says students can design their own experiment where they figure out patterns in the pH of household chemicals. And this is a acid-base chapter assignment. So in that case, when they're just doing some exploration and it's not an actual essential chemistry lab, they're going to want to choose the sensor data path. Here's how that works. So click sensor data, turn on the sensor, it looks a little different, right? And now I'm going to connect from here. It's kind of the same idea. I tap to connect. So pick my sensor. I've already cleaned my sensor. I'm going to remind myself of that. And students are told in that assignment in chapter 16, design an experiment to look for a pattern in pH. So they can come in here and explore. Here are some templates. You could visually see if I click this one, I'm going to get a graph of pH versus time. Table and graph. Well, pH versus time again. Digits, that'll show me pH. Digits and graph. I'll see a digit version and a graph version. That looks pretty good. I might do that. Or I can look under quick start experiments and see if there's anything available for this sensor. And in fact, here's something called pH of common substances. I bet you that's a good idea to test. And this lets me use a table and graph, gives me the manual sampling mode. It's set up to do manual sampling so that I can type in my substance here, tap water. I have also apple cider vinegar. I also have sports drink, which looks identical to window cleaner. So you definitely want to know which is which, and you can figure out by pH. You don't want to be drinking window cleaner that looks like Gatorade. Okay, so now I have the substance names here, and look, it populated the x-axis. Wonder what this display is going to look like. Let's hit start. Ooh, bar graphs. Let me move that legend out of the way. So we got bar graphs here. And I can open up the menu under the bar graph, and I can turn on the tool that gives me the value, which is the same as the value in the table. So I make sure that how much solution do I need for this to work? Just make sure that the glass probe is totally covered. That means anything below that black line there inside of the sensor. So this is more than plenty. And I'm waiting for that sensor to stabilize. I can look at the bar to figure out how much is it moving. Is it stable yet? It's pretty stable. I'm going to click the check mark to keep that value. I'm going to scale the data. Now I'm going to rinse, swish, rinse, blot, and do my next substance, which is apple cider vinegar. So again, a household substance. What is the pH of this thing? And I get a value of about 3. Rinse, swish, rinse, blot. Okay, the next one is sports drink. Wow, that is just about as acidic as apple cider vinegar. Awesome. In fact, more acidic. Okay, I'm gonna rinse that. Rinse, swish, rinse, and blot. And finally, the window cleaner. And here we go. That's a pretty high pH. As it did, that's normally how high it is. And now I've got all my data points. I can hit stop, and students can look for the pattern of cleaners versus food in their data. So that's a whole bunch of different ways to look at SPARKvue. There's a lot more. So I encourage you to go to the PASCO website to look for other types of webinars that go over all the different ways you can use PASCO. So I'm not going to save that data. To wrap up here, like I said, we don't have time for this 3C, but do go check that out. It's topic 3 in PASCO Chemistry Academy, where you use pH, conductivity, and temperature to evaluate whether or not substances are experiencing chemical changes or physical changes when they are mixed. And this is a really nice lab to do at the beginning of the year. Unfortunately, no time to cover it today. So here are some tips that I've kind of already gone over. Here's how high you should fill that storage bottle. Here's the recipe for your pH 4 buffer 4 molar potassium chloride solution. Every 100 milliliters, use your a pH 4 buffer solution and add 29.82 grams of KCl. You can buy it from PASCO. Here's the product number. This all of this stuff is going to be hard to remember. So what I did, all of this stuff here, I put the pH sensor calibration and care information at your fingertips on this slide in your resources folder. So go into your resources folder and find the playlist that has all the ways to take care of the pH sensor and also how do you calibrate the sensor. One of the questions I get asked a lot is, when do you need to calibrate the sensor? Do you need to calibrate it? The answer is you don't need to calibrate it if it seems to be reading fine. And you do need to calibrate it before you do a titration, every time you do a titration. So you'll need a pH 4 and 10 buffer. And if you're not doing anything quantitative, like titration is quantitative, if you're not doing quantitative, then you're fine, probably, probably fine not bothering to calibrate it unless it's really reading a little weird, then you can calibrate it. And then here's the directions on calibration in your resource folder. Other questions about maintaining your sensors. How do I clean these? See all the places I've highlighted pink here? Don't get those places wet with a sanitizing wipe. Everything outside of those areas can be cleaned with sanitizing wipe. So there are different kinds of sensors. There's battery powered, like pH, and there's also like lithium battery on the back. There's a door for the battery, and also rechargeable, like pressure. How can you tell which is which? Well, the temperature sensor, for example, on the screen here, you don't see any USB plug. So, and you see on the back, there's a battery information. It's CR2032 coin cell battery when it needs to be replaced. These, maybe with normal use, you might maybe every couple of years need to replace them. You'll get a low battery light warning. It'll be flashing on the sensor, but you get pretty good lifetime out of these because the sensors will turn off. If students forget to turn off the sensors and they close the software, it'll just turn off on its own. Or if they turn on the sensor but never connect it, it'll turn itself off after 5 minutes. The pressure sensor has a USB symbol on it, and that's how you can tell where to plug in my charging cable. It's right there where that symbol is on the side. So that is a built-in rechargeable, supports USB. So if you forget to charge it the night before, no problem. You can still plug it in via USB and the data will still go to your device as long as you've got that USB connection. Okay, here are the 25 topics for PASCO Academy, and check out the resources that I shared, link for the resources that I shared earlier if you want to see the complete list of them, or go to education.pasco.com and click the Academy link to see them. If you wanted to pick up anything that you saw that you don't have yet, like the sensors, or maybe you're interested in Portal, please contact your regional rep. I'm going to put that link in chat right now. I keep pasting the wrong thing in there. Sorry about that. It's pasco.com support. So that will get you to a regional rep, or you can also get teacher support from there. So for those of you that were able to stick around, thanks for sticking around. I'm going to stop the recording now. So for now, I want to say have a great school year and good luck to you. And thanks for doing what you do.